So we'll begin with our third talk today, Enhancing Knee X-ray Diagnostics with AI. We have Kavya Mohan. She's a data scientist, works at 5C Network, AI for Medical Image Diagnostics. And also we have Naveen K, Principal Data Scientist at 5C Network, AI in Healthcare. So please welcome them on stage.
Hello everyone. I hope you're enjoying the conference so far. I am Kavya Mohan and this is my colleague Naveen. We are here to present about enhancing knee X-ray diagnostics with AI. Today we'll cover the importance of AI in medical diagnostics, particularly in knee X-rays. We'll walk through the workflow of how to build an AI model to predict the abnormalities in knee X-rays. Every step in this workflow heavily relies on Python's extensive libraries. I'm going to show you how Python can enhance medical diagnostics. And this workflow constitutes of DICOM processing using PyDICOM, model training and deployment. And in the end, we'll showcase our product OsteoCheck and discuss its future enhancements. I am Kavya Mohan, a data scientist at 5C Network. My career towards AI-driven solutions for medical diagnostics began at Crane, where I worked on various projects from e-commerce analytics to medical image processing. This experience laid the groundwork for my transitioning into healthcare technology when Crane's team was acquired by 5C Network. At 5C, I've built AI models for X-rays, CT scans, and MRIs, which has significantly improved diagnostic accuracy and efficiency. Now, I am passionate about the potential of AI in transforming healthcare, and I'm excited to showcase our work on OsteoCheck with you today. So, why do we need AI in medical diagnostics, and what are the challenges in traditional method? Traditional method is a time-consuming process. It may delay the diagnosis of abnormality which needs immediate care. In India, there is a shortage of radiologists, say statistics, which can push the clinician to interpret medical scans without any special trainings, which can cause misinterpretations. Even radiologists' interpretation can be subjective, which means it could vary from one radiologist to another. And specialized diagnosis can be limited in remote areas. So how AI can address these challenges? AI-driven solutions enhances speed and accuracy. It also reduces the workload for clinicians caused by the shortage of radiologists. It can analyze large volume of data in seconds. AI results are consistent, thereby it reduces the subjectivity to zero. It also enables easier remote diagnostics. So keeping in mind these positive sides of AI in medical diagnostics, I would like to address the critical need of AI in knee X-ray diagnostics. So before that, I would like to show you the difference between normal and abnormal knee X-ray. In these two images, which image would you tell is a normal image and which one is an abnormal one? Yeah. Yeah, left is an example of normal knee X-ray. Right is an example of osteoarthritis, which has affected 520 million people globally. What is osteoarthritis? Osteoarthritis is a degenerative joint disease which causes the cartilage between the joint space to break down. Furthermore, it makes the joint space to reduce. It can cause severe pain, stiffness, and even reduced mobility. So what are the impacts of osteoarthritis? It has already affected 520 million people globally. Many cases are undiagnosed due to the shortage of radiologists, which forces clinicians to interpret the medical scans, which could lead to misinterpretations. Early detection is the key to manage osteoarthritis. When detected early with few basic lifestyle changes, we can easily manage osteoarthritis. Postmenopausal women are highly vulnerable to osteoarthritis because of their hormonal changes that accelerates bone density loss. This group is at higher risk and can heavily benefit from earlier and accurate diagnostics. This is the progression of osteoarthritis from grade 1 to grade 4. As you can see, the joint space between the two bones reduces until it rub against each other, which could cause severe pain. So if osteoarthritis is detected at early stages, say if we predict osteoarthritis in grade 1 or in grade 2, we can easily manage it by changing a few lifestyle routine, and we can lead a pain-free life. Before we look into the workflow of how to build an AI to predict the abnormalities in knee X-ray, I would like to introduce a term called DICOM, or Digital Imaging and Communications in Medicine, which is a standard for storing, transmitting, and handling medical image information. It contains not only image data but also metadata, which has patient information like gender, age, etc. It also tells the modality of the scan, whether it's an X-ray, CT, or MRI. It also has the capture settings like the date and time of the procurement of scans. This is a short video for you to get a better understanding of what is DICOM. This is Vias is an application which supports DICOM format. So these images are part of two different DICOM files. This is the metadata I was talking about. These two images are known as a study, which is it is one patient's information. We can also do the display adjustment by fine-tuning few parameters in the metadata. So this is the workflow to build an AI model to predict the abnormalities in knee X-ray. First, we'll convert the DICOM format in image to image format, with which we can process it easily through AI. After converting the DICOM, we then move on to annotation. This is a one-time tedious manual procedure that could help us in training the model to predict abnormalities. This is the stage where AI medical experts in 5C would come and label the images, abnormalities in the given knee X-ray images. After annotation, we then move on to pre-processing, where we'll apply certain filters to enhance the image for the model to pick the patterns and learn the abnormalities. After pre-processing, we then move on to model. It has three phases: training, evaluation, and deployment. In the training phase, we would train the model using the pre-processed data with our annotated training data set. We then evaluate the performance of the trained model in the evaluation phase. We have certain thresholds. If the model's performance meet that threshold, we'll deploy that model in production. So we'll look into each step in this workflow in detail. So this is the code to convert DICOM into image. This function takes in input the DICOM file path. We use PyDICOM to read DICOM file, and then we extract the pixel array from the DICOM file. We then convert it into an image. We use PyDICOM for this conversion, for reading, writing, and processing medical images. Why do we use PyDICOM? Because it is solely dedicated to handle medical data. It provides easy access to and manipulation of DICOM. It supports various DICOM formats. It is flexible to adapt different medical imaging systems and standards. So after DICOM conversion, we then move on to annotation. Here, medical experts in 5C would come and put a bounding box, a rectangular box, if they find an abnormality in the given image. These are few examples. This is Label Studio, an open source platform where you can annotate data, where you can import your data and then annotate it. It also supports video and audio formats. So after annotation, we then move on to pre-processing. Like usual pre-processing techniques, we also do normalization, augmentation, etc. But before that, we would apply a filter known as clay. which expands to contrast limited adaptive histogram equalization. It does two things. One, it limits the contrast in few areas of the image. Second, it enhances contrast in few areas of the image. Why do we apply this in an X-ray? In an X-ray, we often diagnose the abnormalities in the bone structure. Soft tissues are not clearly visible in X-ray. To enhance that complex bony structure, we would use this filter. There are two parameters here to play around, clip limit and the tile grid size. You can adjust this and see how the clay filter changes. So you can clearly see the difference between the original image and clay image. This would help the model to pick up a pattern. So after pre-processing, we then move on to the model. We train faster RCNN algorithm to predict the abnormalities in the knee X-rays. Why do we use faster RCNN? Because it balances both speed and accuracy. It also picks very complex things in an image, which is very critical in diagnosing medical image. Knee X-ray often features with overlaying of bony structures. Faster RCNN picks up abnormalities in this, making it ideal for training it for predict the abnormalities in such complex images. So in common, faster RCNN is the latest state-of-the-art model in the region-based convolution neural network family. It has two stages, region proposal network in the object detection stage. In region proposal network, in the given image, random anchor points. Random points in the images are predicted, and these anchor boxes are drawn around these anchor points with different aspect ratios. This anchor boxes might or might not contain the abnormality we tend to predict. This thing is refined in the second stage of the faster RCNN, which is the object detection model. Object detection stage, it classifies whether the anchor box has the abnormality or not, and then it refines the anchor box to confine the abnormality it has predicted. So we use Detectron2, a Facebook AI research library that provides implementations of state-of-the-art object detection algorithm, which also includes faster RCNN. We use Detectron2 to fine-tune the faster RCNN model. Why do we use Detectron2? It is modular, which means we can experiment with different kinds of models and architectures. It has plenty of pre-trained models which we can fine-tune for specific tasks, and it can seamlessly integrate with Python libraries like PyTorch, which makes it ideal to use for both production and research. So to implement Detectron2, you can follow this GitHub repository by Tanner Gilbert, which is pretty easy to follow and work on. So after building our model, after fine-tuning faster RCNN using Detectron2, we then move on to evaluation. We have to check whether the model's performance is good enough to get deployed in a production. We have two metrics to evaluate the model. One is intersection over union, and the other is mean average precision. Intersection over union gives the overlap between the predicted bounding box and ground truth bounding box. Predicted bounding box, we have a separate data set, annotated test data set. We would pass it on to the trained model, and then it gives us the predicted bounding box, and we have the ground truth from the annotation. This IOU gives the overlay of predicted bounding box over the ground truth bounding box. It gives us the measure of how well the predicted bounding box matches with the ground truth bounding box. So this ranges from 0 to 1. Next metric is mean average precision. We all know how to calculate precision in a classification model. We will have positive and negative classes. Precision is number of true positives by actual positives. So how do we find positive and negative classes in a detection model with IOU? If the IOU of the predicted bounding box is greater than 0.9 or above, we consider it as a positive class, or else it's a negative class. We then take the average precision of class of each class for the bounding boxes predicted, and then take a mean from which we can calculate the mean average precision. To summarize, IOU gives us the local accuracy of a predicted bounding box in an image, whereas mean average precision gives us the overview of the model's performance across all classes. So if for a model to get deployed in production, its mean average precision should be 95% and above. If the model passes the evaluation phase, we then deploy it in production. We deploy a model as an API, which takes an image file as an input and gives out a JSON as output, which has coordinates of the predicted bounding box and class of the bounding box predicted. We use fast API to write this API, and then we deploy it using Docker. This is the code for the deployment process. The first snippet gives us the function on how to load the model weights and predict the abnormalities in image. Load the image on the model and get the output predictions as a JSON. And the second one is an API to execute this function. We would deploy it using Docker in production. So Naveen here will give a demo on the product of OsteoCheck, which is built on the workflow which we just discussed. Naveen?
Yep, it's a show time. Let's get started. So I'm Naveen. I'm a principal data scientist at 5C Network, and I've co-founded a startup called Crayon, which has been acquired by 5C. So today I'm going to talk about a problem which have been spoken a lot, like tuberculosis or something, which is osteoarthritis. So let me explain the process to which, from a patient to a doctor to an AI model, how we help. Let's say you have an osteoarthritis. Let's say, I hope not, let's say. So I'm a patient with osteoarthritis. I have a leg pain. I cannot stand properly. I go to a physician. He's like, okay, examining me. And this guy is like, okay, you need to get a knee x-ray. So once you get a knee x-ray, how do you get it? Like, you go to a diagnostic center where they have an x-ray machine. They place it on your knee and they take it. And the outcome is the DICOM, what you have seen. So our AI model input will be the DICOM. And we have multiple models running parallelly. And we'll give you a report which is exactly, it will look like a radiologist report. So I'll explain you the components which we have used there. So once you get the report, you come back to the referring physician and he'll see it and he will take it from there. So this is the workflow which it's going. So when we started to build AI at 5C Network is a 7-year-old company, but we have started building AI for past 1.5 to 2 years. When we started, we want to do something which is actionable, helpful to the community. So also which should be easy to build. It's not like if I go take a chest and build model, it will take years to do it. So knee is simple. It has only 3 to 4 bones, 5 to 6 abnormalities, and it is easy to learn as well. So we started there. And there is also one more reason, as Kavya told. Women's after postmenopausal, like it is likely 50% of the women will get osteoarthritis, out of which almost 90% goes undetected. Let's imagine a woman in a rural village. They don't have much knowledge on this. They're like a simple knee pain. They have a huge bearing strength telling that, okay, it's just a pain of my routine day. Okay. So what we are planning, like how will this product will be useful? This will go in the desks of clinicians and also health checkup, master health checkups. Like chest x-ray, you'll also be taking knee x-ray and you'll have a knee health report. So this is what the product is and how it is useful to the people out there. Now I'll show you the workflow. So let's say I'm the doctor. So I've got a beautiful sign-in page. Now what I'm going to do, I'm going to add a scan. Let's say patient name Vimala, age 57, gender is female, mobile number something, referring doctor is myself, Dr. Naveen. Okay, history is knee pain since a year. Okay, now this has two input type, as Kavya has spoke about DICOM. The input can be either DICOM of or image. Here for simplicity we have image. Once you have DICOM integration with us, we also accept DICOM. Now this X-ray is getting processed by our AI model. So what do you mean by AI model here is, let me break this up. So once I get an X-ray, I check whether it is an E-X-ray or not, first part. The second part is, like, I'll tell whether it is reportable or not. What do you mean by reportable? So in India, there is a huge problem of artifacts, like rotating your knees while the X-ray is taken. The machine is not proper, the specifications are not so great, stuffs like that. So it will check for that. Next, it will try to segment both left and right knee if present. If there is only one knee, that also it can take it up. Once it is segmented, it will focus on the main parts, like which is the junction of your knees. So it will crop out for both left and right knees. And it will start, like we have individual pathology models, like we have almost 6 pathology models. Each of that will get processed. Like we have multiple detection models out there as well. So, and this is how the output looks. If you see here, it has both left and right knee. So there is a condition called osteophytes, which is like just a bony projection on your left knee, which is okay. But if you go for on your right knee, so like this is way complex. Okay, so there is a sclerosis, prominent tibial spike, osteophytes, and everything, reducing joint space. So once this get detected, it gives a comprehensive observation and impression. Okay, so like this is how the product is. Like you'll get also, in order to this, you'll be getting lifestyle changes what you need to make, because grade 1 osteoarthritis can be treated easily with few physical activities and few vitamin tablets such as. So this will be your starting point where you can take it, like if it is grade 3 or 4, they'll just do total knee replacement. And like this is a diagnostic test that we took for sorry for the Slack message. Okay, that we took for this basically focuses on the rural population. How can they get to know early stages of osteoarthritis? So if you have any questions, I can answer it up, and let me ask Kavya to jump in and finish it.
So we have used 640,000 knee X-ray images to train the models which we saw in the osteo product. These are the metrics. The first column, pathology, has the abnormalities of knee X-ray and the mean average precision at 0.9 IOU, which is above 95%. So this is the grading of osteoarthritis classification model. The precision and recall of this model is 95.6 and 90.5 respectively. So the impacts of AI implementation. Before implementing AI, the overall knee X-ray diagnostic accuracy was below 92%, and the osteoarthritis grading was below 86% due to subjectivity. And after implementing AI and iterating the models over months, we could achieve the accuracy of about 99% for both overall diagnostics of knee X-ray and also the osteoarthritis grading. So with this data, I can say that that we have improved the quality of knee X-ray diagnostics. Knee X-ray diagnostics has become more efficient and effective. So expanding the workflow which we saw today, we can apply this same workflow to detect the abnormalities in different organs also. Like we can use it to detect abnormalities in chest X-ray, spine X-ray, etc. This model is scalable to analyze n number of images. We can also analyze large volume of data in seconds using this deployment workflow. And this unified approach is easy to implement, and whenever any new medical diagnostic need arises, we can easily modify our approach. So this is a Kaggle open source data set which you can try on. It has 15K chest X-ray files, chest X-ray DICOM files. It also has annotated data for around 14 classes. So you can implement the pre-processing technique which we discussed here and use Detectron 2 to fine-tune faster RCNN, and then you can deploy it as an API. Thank you. If you have any questions, you can come to that side of the stage and we can take that up.
Hi. Yep. So in the data collection process, the radiologists themselves don't agree on, bounding boxes all the time, right? So when you're pushing that into training, how do you manage different radiologists giving different bounding boxes, let's say?
So our annotation team is structured in a way where like it's not only radiologist, it's also a technician who has done BSc, MSc radiology. So we'll have one radiologist who will be training all them on this particular scans. It's not like we give like $20 or $30 to radiologists and we'll get data. It happens in a controlled environment, and we recheck it twice, thrice, like even like 4 times, because our base data set is limited. Like it's like we have scaled it through a lot of different other approach. The base data set, which consists of some X amount of images, it's like the most accurate images. So it's done on a controlled environment. So that's the reason.
So another question is about data distribution shifts, like the data that you push into a model while training may not be similar to the data that you see post deployment, right?
Right.
So how do you deal with that?
So yeah, that's a good question. Since like 5C have been doing this business for 7 years, so we almost have scans from all over India. So we don't have any like scans outside India, so which covers literally all states. And we ensure it is like we have, based on the metadata, we know from which state, which city we are getting this data. So from that, we ensure the proposition is right. Thank you.
Hi, this is Santosh. Just want to check how widely is this being accepted, because 90% recall in rural areas where there is no radiologist with just one physician who is actually referring this, and he may not completely understand. But what if you are missing, which is an osteo, whatever the disease, right? So what if you are missing it? And what happens next? As in, what if it is not detected with 90% recall? How widely is it being accepted by doctors and physicians?
Right. Since this test is not something, it's like for diagnostics test, of course, the decision goes on the referring physician. So the accuracy which you have seen is for all osteoarthritis grade. It's not for grade 1 versus grade 4. So if you're miscalling grade 4 as grade 1, then that's a blunder. That we don't do. Grade 3, grade 4, there is a subjectiveness. The treatment plan doesn't change much. Grade 1, grade 2, the treatment plan doesn't change much. So it's like we also have evaluated, and the model is nearly 99.5% accurate on grade 1 versus grade 4. So that will help here. So it's not involved in any major decision. So it's likely to be a diagnostic test.
Just one more question.
Sure.
This is definitely not life-threatening, right? So any plans of implementing it for, say, brain stroke, where it is like really definitely, I mean, a decision can be taken and then the disease can be diagnosed, right? So any plans for that, and what is your thought? Because data definitely is not there for that. And I also want to understand, how did you collect data for this, or how many physicians were actually, radiologists were actually helping you out? And yeah, what was your base data set?
So the thing is, right, so we ran we are still running teleradiology business for almost 7 years. So we have 8 million scans along with the reports. So basically, first we started as a teleradiology business. We sourced all data. Now we have them to like build AI models. So that's our strength. And to answer your second question on stroke and bleed, so I get it. Like detecting bleed in a CT brain is literally, it's I won't call it as too tough, but the problem here is, right, so the technician who's like procuring scan, he himself can catch bleed, right? So like we can use it for documentation purpose. Like it's not like we are not working on it. So we already have a CT brain model which will tell whether it's normal, abnormal. If abnormal, we are detecting almost 14 pathologies to classify bleed, types of bleed, infarcts. From that, literally everything we have it. So the reason, like, we need some more time, like, to fine tune it. It's not like there, it's not a finished product, but it's a good POC that we have done. It's been launched with few hospitals as well in India, so we are doing a POC. But yeah, that's like emergency trauma. Like, we have a separate wing which focuses on this. Not only like we do MRI stroke protocol, all those things, we focus on emergency as well. So this is something like on a safer side, where as a product it can scale much. Right. It's not like, okay, even a minute matters in case of a hemorrhage. The thing here is, right, so on a conventional setup, let's say whenever the scan is procured, the first, the radiologist will look into it. It's not like they'll give report after 4 hours. They type report after 4 hours, they look at it, they look into it on the minute, on the second of the scans procured. So it can be helpful in routine test where if you caught something in CT brain, something like that. So we're building it. The thing is, like, it's a tricky problem statement to put it on forward. So it has few other complication as well from the implementation side. Again, right, so if I build a model for CT brain, which is like 5 GBs of data, where will I deploy it? I cannot keep GPUs on individual places, right? So it's been like, we are exploring it. Soon, like, we'll have a solution for it. Thank you. Cool. One more question, can I? Okay. We can take it up. I'll catch you. Thank you, everyone.